Welcome to using propensity score modeling to create equal comparison groups. It is my pleasure today to introduce today's presenter. Christopher Campbell is an assistant professor in the Department of Criminology and Criminal Justice at Portland State University. Dr. Campbell's research emphasizes the compilation of basic and applied research to generate cumulative knowledge for the sake of improving the justice system with a base of empirical evidence. The majority of his work consists of evaluating policy and practice in community and institutional correction strategies within adult and juvenile correction settings. He's also served as a consultant for the U.S. Department of Justice on racial bias in policing and policing use of force analyses, as well as the impact of sentencing on recidivism, and as a consultant for state legislatures and departments of correction. Throughout his research, Dr. Campbell places great importance on the use of mixed methods to investigate research questions, but emphasizes quasi-experimental designs using propensity score modeling. So I am so glad that we have him here today to teach this course to all of you. With that, I'm going to take myself off camera and turn things over to Dr. Campbell.
Thank you, Susan. I appreciate that. Going to make sure I'm showing the correct screen here. All right. Susan, can you see that all right?
Yes, that looks great. Thank you.
Great. All right. Thanks again for everyone for attending. I welcome you to this basic training on propensity score modeling and how to use it to create equal comparison groups. Today's discussion will be a basic overview of PSM. As Susan mentioned, I'm a researcher that often applies PSM to several different settings. And I'm here to share what I've learned along the way in hopes that it can help you in your application. It's important to note that it's simply not possible to cover everything about PSM in this short time. So I'm going to touch on just enough to get you familiar with it if you're not already. And if you are familiar with it, then this is hopefully going to be a good refresher, but also you'll be able to pick up something that you hadn't known before, hopefully. And I aim to touch on a few of the major areas of debate and discussion, and some of the extensions that we've seen in the discipline and other disciplines, largely the medical science fields. So without further ado, I'll go ahead and move into some of the substance. A quick basic overview of today's course. We'll begin with a discussion of the conceptual background of PSM and things we always need to keep in mind when we use PSM, particularly when it comes to simulating a randomized control trial. Then I will discuss some of the basics of PSM, including assumptions and the workflow when applying it. After that, I will move into some of the specifics related to calculating or conditioning the propensity score and some of the techniques that are used to do that, as it's become a bit of a hot area of debate. Then we'll move into discussing some of the balance approaches, or how balance is measured and how to assess it. Following that, we will discuss some of the more common approaches to employing PSM, such as matching, stratification, and weighting. And I will then touch on the need to reassess the balance to know when you're actually successful when using PSM. Then we'll cover what PSM means for the outcome analysis and isolating the treatment effects. And last, I will touch on just a few things that have been developed and extended from PSM within the techniques and the ways to assess the propensity score, or at least calculate it. Important to note here that while everything that we'll be discussing is of course important for all PSM applications, regardless of the treatment type, we will focus our attention today on the application of PSM in relation to binary or dichotomous treatments, so whether or not someone got the treatment. I also want to note real quick that, as Susan's mentioned, I've worked in just about every area of the system, so policing, courts, and corrections, and while most of my application examples today are focused on corrections-related examples, there are applications of PSM in just about every area. of criminal justice, and many of the articles that I've tried to make available to you at least one of them touches on each area. So they're worth checking out if if these examples don't necessarily resonate with you. So the conceptual background of PSM stems directly from what we are trying to achieve in simulating a randomized controlled trial, or RCT, for the sake of uncovering some type of causal relationship between our treatment condition and the outcome of interest. The goal of virtually all exploratory research, including evaluation research, is to answer the causal question: what is or was the treatment policy or practice effective in impacting the outcome of interest in the intended way? In other words, did the treatment work? In order to know whether the treatment had an effect with a high degree of confidence, we need to isolate the potential effects of the treatment by only allowing two values to vary: the treatment indicator, that is whether or not you got the treatment, and the outcome. Of course, we always need to keep in mind the three criteria of deciphering causality, which is temporal ordering, ensuring that the treatment precedes the outcome; association, that there is an observed bivariate relationship between the treatment and the outcome; and ensuring that such a relationship, that association, is non-spurious, that is, it's not caused by some other factor. Non-spuriousness is a key threat to causal inference that we must account for either methodologically or statistically. This is the purpose of designing rigorous methodology and employing complex statistical tools so that we can ensure that the degree of spuriousness is measured. The goal is always to isolate the effect of the treatment on the outcome. So let's say that we have a treatment condition that involves a rehabilitative program that has been employed for people who are preparing to leave prison. We want to know if this program can reduce recidivism. One of the major factors we might want to account for is the presence or severity of a mental health disorder. Correctional theory and the principles of effective intervention would suggest that in order for a program to be successful, it should be responsive to how individuals learn, which having a mental health disorder may impact. The gold standard to isolating the effects of treatment and methodologically controlling for spuriousness is through random assignment, or what's known as the randomized controlled trial. This slide provides a basic breakdown of the flow and expected outcome of a successful RCT. In a properly executed RCT, there is no association between the potential outcome variables and the assignment to the treatment. Moreover, the problematic factor we just identified, having a mental health disorder, would be equally present in both the treatment and comparison groups if the RCT is successful. RCTs are often not possible, or sometimes they're simply unethical, especially for criminal justice researchers, as you all know. So spurious relationships must be controlled for in another way, such as statistically. Regression can help hold these confounding factors constant while estimating the effect of the treatment. And this was traditionally the approach for a long time, up until the late 90s or early 2000s, really. However, regression can only do so much, as it inherits existing selection bias. Regression cannot account for the selection bias, such as reasons why certain people are getting the treatment. And so in this example, maybe there's a discretionary decision regarding individuals with varying traits who are given the treatment, which makes the treatment cases different from possible comparison cases. The regressions will not only inherit this bias, but will also favor the larger group. So if your comparison group is substantially larger than your treatment group, then it's going to favor that larger group. Also, it can be rather difficult to tease out differential effects of the treatment, often because we're comparing people who look very different. Regression is limited in its ability to identify this variation, which is known as the treatment effect heterogeneity, which are reasons why certain people might respond differently to the treatment. Without accounting for, first, reasons why certain people get the treatment, and secondly, how differences exist between the treatment and comparison conditions. These are often referred to as naive models or naive estimates. While it may be correct, your regression likely isn't accurate because it isn't complete. Moreover, in order to appropriately account for the treatment effect heterogeneity, we need to differentiate between types of treatment effects. Treatment effects, otherwise known as estimands, are estimates of the treatment effect on the outcome given a counterfactual condition. Generally, there are three estimands we refer to and are interested in: the average treatment effect, or the ATE, the average treatment effect on the treated, the ATT or ATET, and the average treatment effect for the untreated, or ATU. These represent the average difference in the outcome between the treatment and comparison groups we should expect to observe if under certain conditions. So the ATE is the average difference in the outcome between treatment and comparison groups we should expect to observe if the treatment were applied to a randomly selected people in the target population. For example, if we selected a random adult in custody and applied a cognitive behavioral treatment to them, regardless as to whether or not they needed it, what would be the expected average difference that we should see? So the average treatment effect for the treated is the average difference in the outcome between the treatment and comparison groups we should expect to observe if we could randomly select a treated case and observe the outcome if we took away the treatment, thereby viewing that person's counterfactual condition. This is essentially, if we could see an alternate universe in which that one person, that exact person, did not get the treatment, this is essentially the ATT, or what we're trying to isolate. The ATU is the average difference in the outcome between treatment and comparison groups we should expect to observe if we could randomly select an untreated case and observe the outcome if we actually applied the treatment to them. So it's the same alternate universe idea, except we're grabbing somebody who didn't get the treatment and say, well, what would this person look like if we did actually give them the treatment, that exact person? It's important to note that the ATE, ATT, and ATU are all quite different, and it is critical that you know which one you're speaking about in your conclusions about a particular treatment. ATE is actually a weighted average of the ATT and ATU. Although everyone wants, or at least they think they want, to know the ATE, the average treatment effect, because it's that kind of sexy term, it is often not possible or not as useful as the ATT or ATU. Now, this is especially true when you trim some of the cases while employing PSM, which we'll get to in a bit. As soon as you trim cases and match comparison cases to the treatment, the ATE really no longer is that meaningful, because you are tailoring your comparison group to look just like those who got the treatment. Thus, you're really exploring the average treatment effect for the treated. In successful randomized controlled trials, the ATE, ATT, and ATU are all the same, because it removes the baseline bias and overall treatment effect heterogeneity, really, or controls the treatment effect heterogeneity. Individual differences will still occur, but the average is going to be accurate. Absent a successful RCT, we try to simulate this by removing selection bias from, or using PSM, in order to ensure that we are observing effects actually attributable to the treatment. In removing the selection bias, we also structure and somewhat control for treatment effect heterogeneity as we emphasize average treatment effect for the treated. Experiments are so effective at isolating the treatment effects because randomized assignment, the random assignment, systematically builds the necessary counterfactual group. PSM's primary purpose is to remove selection bias and provide an unbiased estimate of the treatment effect. If this is done correctly, it creates that counterfactual by balancing the treatment and comparison groups on the treatment group traits, thus simulating a version of the randomized control trial equal by creating these equal comparison groups. But we cannot account for the unobserved factors, which I'll highlight in a bit. The average treatment effect for the treated, and average treatment effect for the untreated all depend on the emphasis of the PSM approach. Some weights can be created to estimate the ATE, but the overwhelming majority of the applications and conclusions are focused on the average treatment effect for the treated, and therefore will be the assumed estimate throughout this presentation. So to begin thinking through whether PSM is appropriate for your evaluation, you must consider what the treatment is, what you expect to see in the outcome, and the information at your disposal. And this, I pose these questions here, not because I don't think many of you already know this, because I think a lot of you do, but if not all of you knew this already. But I think these are good questions to also posit to the practitioners at the line level, or even at the policy level. When they're asking questions like, does this program work? You need to make sure that they recognize that they need to have answers for these as well. And if they don't, then there's a chance that you might not be able to use PSM or even evaluate the program. So you need to have clear answers for the following questions. How does someone get into the treatment? What is the eligibility criteria to actually be in that eligibility pool to receive the treatment? And for the outcome, you need to have clear answers to the questions, what does success or failure really look like? What factors besides the treatment condition might impact that outcome? As we think through what is important to account for, we can start with thinking through the traditional regression model that we might use to predict the outcome. Traditional regression applications predict the occurrence of the outcome while controlling for other observables, including whether or not someone got the treatment. We also have to think about how people are assigned to the treatment, and can we measure the treatment eligibility? The process by which people are assigned to the treatment must be captured or modeled. If we can't model this to a reasonable degree, it's possible that there's too much arbitrary variation or variation in the unobservable measure or unobservable measures to identify a suitable comparison group. We also need to keep in mind that there is likely to be some overlap between the process by which people are assigned to the treatment and other factors related to the outcome, such as sex, sometimes race or age. We will talk more about this overlap in just a little bit. We also must be cognizant of the unobserved, as it always has a potential to impact our findings. The best way we can do this is to keep in mind the question, what else could be examining the selection or explaining the selection bias? This lends greater credence to choosing the most appropriate models when conditioning the propensity score. Another point to touch on before addressing PSM specifics is ensuring that you are asking a question that is answerable using PSM. If you're trying to isolate the effect of a specific intervention or trait, PSM might be appropriate for you. In this sense, your specific question is, what is the effect of the treatment on the outcome, or does this treatment work the way it should? If you're more interested in identifying factors or predictors of an outcome, then regression might be all you need. In this sense, your question is something like what are all the factors that can cause a change in the outcome? And the treatment might be one of those, but that's not quite the same as is this treatment effective at doing what it's supposed to be doing? We cannot forget, though, regression estimates will be biased when using biased data. Remember that they inherit the bias. So we shouldn't just assume that throwing the treatment variable into a regression will produce a reliable, unbiased estimate of the treatment. What you're doing there is if you include the variable of whether or not somebody got the treatment in the regression, you're recognizing whether or not there's actually a strong association between the treatment and the outcome potentially, given all these other factors. But without controlling for that selection bias and treatment heterogeneity, you're not going to know the magnitude or the impact of that treatment on the intended outcome. Whether you're applying PSM or not, you will likely be estimating a regression in the end. We'll talk more about this later in this what's known as double robust approaches. But the key thing here is to determine what you're most interested in, which is either considering causes of effects or isolating effects of causes. Regardless of what you choose, the unobservables can still influence your findings in a way that would not be an issue in a successful RCT. A successful RCT will always be better because it randomly assigns the unobservables. PSM could be appropriate anytime there is the potential for selection bias or there is an imbalance between groups to be compared. Some examples of this include a retrospective analysis. This is probably the most common form of how PSM is applied in criminal justice evaluations. And this is where we are essentially matching and comparing a historical group that would have been eligible for the treatment to the current treatment group experiencing the treatment as we see it today. The idea here is that had the treatment been available back then, these individuals would have gotten it, and therefore they're an eligible comparison. Another application is using PSM to improve balance in a field experiment. So if you run an RCT, or if you've ever tried to run an RCT, you know that there are about 100 things that could go wrong in the random assignment process, and you might be able to anticipate about half of them if you're lucky. With bias finding its way into your comparison and treatment groups, PSM can be employed to correct that bias. And this is actually quite common, especially in the medical field. When something goes wrong with an RCT, you'll often see some application of PSM in order to correct it. Another way to use PSM is in balancing groups to isolate the effect of one measure. I gave you the examples here of demographics because this is a growing area, especially given concerns over equity and how the system is applied. Sometimes people have a hard time wrapping their head around this because they think you can't randomly assign someone to race, so how is this applicable? Well, there's no selection bias to remove in that sense. And while this is true, however, that's not really the question that we're asking in this type of situation. Instead, what we're asking is, given two groups of people who are equal in virtually every way except their race or gender, what is the difference in the outcome? So that's where we can use PSM to actually answer that type of question. The caveat to all of this is that you must know and have data on as much as possible about the treatment condition or that variable that you're trying to isolate, or how people are assigned to that treatment condition if you are looking at a treatment, because PSM, generally speaking, is data hungry, or commonly known as data hungry. So the more data points you have, the better off you are. We also must be sure to keep in mind factors like the sample size that's available to us, the areas related to the treatment eligibility, and potential need for examining cohorts. In doing so, we have to think about whether it makes sense to actually compare certain groups of cases based on what they've experienced. In terms of the sample size, we ideally want a comparison group pool that is twice, if not 3 times the size of the treatments, ideally. This is because eligibility criteria and certain matching techniques make it so that there are a lot of potential comparison cases that we end up trimming out of the sample to identify the best balance with the treatment group. It is worth noting that you should conduct a power analysis to know how many cases you actually need to detect a treatment effect. Also, it's worth noting that my colleague and I, Dr. Ryan Lebrecht, and I recently received an NIJ grant to examine how well PSM techniques actually can replicate the findings of the criminal justice randomized controlled trial, or RCT. And after our test, about seven different techniques, we found that PSM was quite close and robust to small samples. So the smallest treatment group that we used matching or propensity score modeling on to replicate the RCT findings and was successful was about 67 cases. which bodes well for especially a lot of treatment conditions that have a lot of dropouts or you have very few completers. Another thing that we need to keep in mind is that eligibility criteria can shift over time via statutory and discretionary changes. There are many other programs, there may be other programs implemented and dropped during this time frame from which you're looking to draw your comparison group. Additionally, cohorts may be critical to break out in the treatment condition, depending on how the treatment changed since the rollout. Not to mention, the rollout period should be considered as either its own comparison group or potentially omitted altogether. It really depends on how the program was rolled out and how intense the fidelity of the treatment was. And that's something that we won't touch on today, is fidelity of the treatment. So you're assuming, of course, that the treatment is being applied the way it ought to be applied. With all the conceptual framework stored in the back of our heads now, we can now start thinking about the basics of propensity score modeling. So a propensity score is the predicted probability of being in the treatment condition given all observed covariates. As you can imagine, it is pretty critical to know as much as possible about what goes into the assignment process. As we think of these factors, we need to consider what goes into a predicted probability. So as the nature of a propensity score, as is the nature of the propensity score, most of the methods used to model the selection bias rely on calculating predicted probabilities of being in treatment. And one of the most common and basic methods of calculating the predicted probability is through a binary logistic regression. I know many of you had already indicated that you are familiar with logistic regression, so I'll ask that you bear with me for this slide as I highlight a few of the basics of the predicted probability. Binary logistic regression is the basis of much of the conceptual background for propensity scores, or P-scores, or I'll often refer them as PS, just an abbreviation for propensity scores. So the propensity score is trying to predict the dependent variable that is, of course, dichotomous, and in that sense, it's the dichotomous treatment. So the model uses covariate values to predict a threshold, or tau, of when someone is likely to receive the treatment, answering the question, at what point on the x-axis here at what point on the x-axis does the y-axis go from 0 to 1? 0 being not receiving the treatment, 1 receiving the treatment. The probability is computed using maximum likelihood estimation, which you can think of as fitting a regression line based on observed values most likely in the event that the event occurs, which would be the treatment. The regression line, so to speak, in this sense, is observed as an S-curve. The steeper the middle of the S is, indicates the better the predictor. The curve connects the observed codes, so in this case, the number of prior drug arrests shown in this graph here, within the probability of receiving the treatment coded in 0 or 1. As you can imagine, the better a model is at predicting when a case receives the treatment, the more precise the PSM technique will be at finding a comparison case and estimating the treatment effect. Therein lies the crux of some of the debate that goes around how we condition or create or calculate the propensity score. This is a good point to discuss the core assumptions of PSM, which we'll move into now. So there are 3 core assumptions of PSM. The first is commonly referred to as the strong ignorability of the treatment assignment, but is also known as selection on observables, the conditional independence assumption, or CIA, or unconfoundedness. None of these are relatively easy to say, but they essentially state that the observed outcome differences are attributable to the treatment when covariate values between the treatment and comparison cases are the same. Thus, the treatment assignment is strongly ignorable if the probability of being assigned to the treatment, conditional on the observed covariates, is independent of the outcome. There is no direct test for this, so it basically pans out to if the probability of receiving the treatment can be successfully modeled using the observed covariates, then this assumption is essentially satisfied. Thus, it is critical that the selection bias, that is the treatment assignment process, can be appropriately fit by the propensity score model. So it's essential that the initial logistic regression, or whatever you're using to condition the propensity score, be fitting the data properly. The second assumption is that there is some degree of overlap in the probability of receiving the treatment between the treatment and comparison cases. So the comparison group cases must have a non-zero probability of receiving the treatment. In other words, if you don't have eligible people in your comparison group that could have received the treatment but didn't, then you cannot really compare those groups. One violation example might be trying to assess the effects of solitary confinement. Now, before you say, hold on, there are a few studies out there that use PSM to assess segregation effects, and I realize that. And I'm not calling those studies into question at all. But what I am saying is that particular scenario is a very difficult one. It's particularly difficult because there really cannot be a historical comparison group because we've been practicing segregation for so long. And finding eligible people who did not get segregation is really tricky because you really had to do something in order to get into segregation. So it really depends on maybe the institution's process, the facilities process of how someone actually gets placed in segregation. If you can model that, you're okay. But you really got to be careful, because if you're not careful, PSM may not be able to provide unbiased estimates of the effects of solitary confinement in prison because the comparison group typically has a zero probability of receiving the intervention, that is segregation. The third assumption is the stable unit treatment value assumption, or SUTVA. This assumption states that whether or not a case receives the treatment does not influence the potential outcomes of any other case. So in other words, there's no interference or there's no contamination. Furthermore, all treatment variations are accounted for and comparable across all treatment cases. So there's no real variation in the treatment. This further highlights the importance of dividing the treatment into cohorts if necessary. So if the treatment has changed over time, or if you've had to truncate a couple of weeks off of cognitive behavioral therapy because you just don't have the time, or you've been allowing people to jump in, halfway through the course, there's a question as to whether or not they're actually getting the full treatment. So if there's a variation of the treatment, you need to account for that in some way. And cohorts is a good way to do it. A couple examples demonstrating how this can be violated include providing too many housing vouchers for people reentering from prison may remove housing for comparison group cases. And this could be an example of interference, especially in rural counties. Another example of a violation of SUTVA is how some cases receive cognitive behavioral programming that was 6 weeks long instead of the 8 weeks long. So that's the variation of the treatment that I just described. So now we're going to start getting into some of the more specifics related to PSM. And in order to keep our collective minds wrapped around what I'm talking about, I'm going to use this diagram in various ways throughout the presentation. Along with this will be the traditional workflow of applying PSM, which will largely focus on breaking down this half of the diagram. To break out the traditional workflow, we will slide this diagram over and zoom into on the steps that we're specifically talking about and needed. So the traditional approaches, and indeed many continued approaches that we still use, many people still use today, in applying PSM relies on appropriately modeling the selection bias and perpetually checking the balance between the groups. First, we need to consider the factors that are related to the treatment assignment. And some of you may be wondering, can't we simply identify all the factors that predict the treatment by running a regression? And to that, I would say, not yet. First, organize all of the observables that you see so that you can see where they fit in relation to the treatment and the outcome. This is easy to forget about because of the way that confounding covariates can play a part in both the treatment assignment and the outcome. So let's say, as an example, and I'll walk this one out a little further. Let's say that we're trying to evaluate a reentry program for adults being released from prison to identify to what degree it can reduce recidivism, if at all. This program was implemented years ago, but the legislature wants to know if it works to keep people out of custody. We first need to consider eligibility factors. For most criminal justice related programs, there is statutory eligibility and discretionary eligibility. So that which law or policy dictates someone will be eligible versus when somebody such as a probation officer or a case manager has the ability to say this person would do well, this person wouldn't do well. We need to make sure that we account for anything that creates systematic eligibility criteria. For example, maybe the program requires the individual must be nonviolent, high risk, and high need. Considering what is collected and how it helps guide the eligibility, we need to know that it is possible that the high risk and need aspects of an individual are determined by a dynamic risk assessment, such as the level of service case management inventory, or the LSCMI, which is an off-the-shelf fourth generation risk assessment. Which policy, in this case, maybe policy dictates that it's collected at intake to prison, it's collected at release, or it's supposed to be, and then every 6 to 12 months after that while the person's in the community. We definitely want to include information from the LSCMI scores prior to release. This has a lot of information on dynamic risk factors, such as antisocial associates, drug use, etc. So this is definitely something that we want to know. But we need to be cautious of where the variables are collected in relation to the temporal ordering and what could be impacted by the treatment. Considering that the LSCMI is collected after release and every 6 to 12 months in the community, we do not want to include information from the post-release LSCMI scores and domains in the propensity score. Conditioning the propensity score on a factor that could be influenced by the treatment could mask the effects of the outcome. This is why you should not condition the propensity score on post-treatment variables. And just for those who are not familiar with the LSCMI, there's a lot of domains in there. If you're collecting it at multiple time points, depending on the type of the treatment, so in this case, there's cognitive treatment embedded in the treatment condition, that cognitive treatment or other factors within the treatment might actually influence a change in someone's LSCMI scores. So if we bake that into our propensity score, we're going to be washing out some of the effect of the treatment on the outcome. So instead, we can include these factors, the post-treatment factors, in a post-BSM analysis, which we'll discuss later. So once the measures are organized temporally, we need to calculate the propensity score. And assuming that you have more than 10 variables or so, there's an ongoing debate over the best way to choose the covariates to use to condition the propensity score. One of the most recent PSM approaches that I employed had over 300 covariates. And while this is not ordinary, this is not common, if you have more than 10, and typically you want to dichotomize, if they're all categorical variables, you want to often dichotomize every category just so that you can ensure that each one is accounted for. This can kind of blow up the number of variables you might have to choose from. So the first way listed here is the practical rationale, which is where you include the variables that are factors related to discretionary and statutory eligibility. And this should always be included as best as possible. The next two involve identifying measures that are different between the treatment and comparison groups. This could either be including only those that possess significant differences, such as through a t-test or a chi-square, or those that possess a standardized percent difference over 10 or 20%, which we'll discuss soon. But it's similar to significant differences rationale, whereas if it's above 10 or 20%, then you definitely need to include that particular covariate in the model of the propensity score. The fourth one here is just simply known as the kitchen sink approach, and that involves all available measures so long as they come before the treatment. And this is largely criticized as being atheoretical, but a lot of people who rely on PSM in other fields such as education, epidemiology, et cetera, they will often go the kitchen sink approach because their goal and their rationale is, well, we're trying to bake in the best balance possible. Why wouldn't you want to use everything? To which people will say, well, sometimes it doesn't make sense to include that in the ongoing debate, et cetera. The fifth option here goes kind of hand in hand or is largely associated with the kitchen sink approach, which is using machine learning regressions such as lasso regression or ridge regression to determine the best fitting measures. Often, regardless of the debated method, the right one is the one that provides the best balance for you and that you can justify and work through, making sense theoretically. Ideally, you want to test all of these approaches, really. And I tend to test all of them or assess all of them whenever I'm conditioning a propensity scores, just so because I like to leave no stone unturned. So, I will build confidence in my models. Ideally, if you can do this, that's great. However, that's often impractical. So it's highly recommended that you take stock of what you know about or have measures capturing how cases are assigned to the treatment. The less knowledge and data that you have about the treatment assignment process should be supported by more robust methods of selecting covariates. So if you don't know much about how people are assigned, or you think that there's a wide variation in discretion, perhaps, among practitioners, and you have a lot of variables to choose from, then you might want to lean more towards this kitchen sink or the machine learning regressions, while still associating or ensuring that you have something related to statutory eligibility at the very least. That being said, regardless of how much you know, significant differences should also be used, or should always be used, with great caution. So these t-tests, the chi-squares, any type of Neiman-Pearson approach to null hypothesis testing, which we'll talk about in a little bit, you should be used with great caution because these are largely sample size dependent, and the standardized percent bias should always accompany this particular method. So with that, we'll move into conditioning the propensity score and discussing where that fits in and what that looks like. Once we've selected our measures, we need to fit a model predicting the probability of being in the treatment group, such as in a logistic regression. Now we need to calculate or condition the propensity score, and there are a few ways to do this, as I just kind of highlighted before when talking about machine learning. But this is another area of hot debate as to which one you should be using to actually condition or calculate your propensity score. So while logistic regression is the traditional approach to capturing predicted probabilities, recent studies have highlighted how it can be inadequate as it's heavily dependent on the base ratio of treatment cases to comparison cases. Smaller proportions of treatment cases decreases the model's accuracy in how well it accurately classifies when somebody gets the treatment. Typically, those models are often, if it's a large comparison group pool compared to your treatment pool, what it's doing is correctly classifying how often somebody doesn't get the treatment. A handful of scholars who use propensity scores often in their work have argued that logistic regression is no longer being used by academics and practitioners alike. And I'm afraid I have to share that I don't really share this perspective. My colleagues and I are conducting a systematic review of PSM in criminology and criminal justice studies. These are peer-reviewed studies. And among the 36 that we've gathered and analyzed so far, ranging up through 2020, almost 75% of them rely on logistic regression to condition the propensity score. So in spite of what my colleagues might believe, I don't think that there is actually a movement away from logistic regression. And I think this is going to actually be larger the more we look at technical reports. So when a lot of folks from agencies like your own might be employing PSM, you're likely using logistic regression. And it's not necessarily the case that it will always be problematic. It should just be noted that it can be problematic. Boosted regression is one of the approaches thought to yield greater accuracy in predicting when somebody gets the treatment. It uses machine learning, specifically random forest techniques, to estimate complex models iteratively to find a good fit that doesn't depend on linearity or the additive nature of measures used. The problem is that the iterative algorithms like this must have some type of stopping logic. And generalized boosted modeling does not have the best stopping rules. The user must indicate the number of iterations the model uses, and in doing so, it becomes a guessing game. General practice suggests that you should use no less than 5,000 iterations if you're using these, and then assess the mean standardized percent bias of the treatment and comparison groups. While this is a great tool, and I have used boosted regression before, it has the potential to dramatically increase the accuracy of the propensity score, which of course will help to remove bias. There are times in which it does not perform well. Sometimes it doesn't even perform as well as logistic regression. And it is hard to tell when this will be the case. So I think the jury is still kind of out on its necessity in calculating a propensity score. The last here is the covariate balance propensity score, which is used to exploit the dual characteristic of the propensity score as a covariate balancing score and the conditional probability of the treatment assignment. The estimation of the CBPS is done with a generalized method of moments or empirical likelihood framework. We find that CBPS dramatically improves the poor empirical performance of propensity score matching and weighting methods reported in the literature. If the propensity score model is misspecified, which often is the case because there are a lot of unknown factors we can't model, the covariate imbalance or bias can result. One of the problems with using logistic regression with PSM is that some measures that were balanced before PSM is applied fall out of balance after PSM is applied. This problem doesn't really occur when using CBPS. Covariate balancing propensity score estimation minimizes imbalance and maximizes prediction of the treatment selection simultaneously, making it so that the CBPS is more robust to any misspecification. Personally, I will still run all three of these and recommend to you to do the same if you are able. And then I choose the most efficient one that reduces the balance the most. About 95% of the time, I go with CBPS. Regardless of which we choose, we need to make sure that we fit the model appropriately to ensure that we minimize misspecification and therefore minimize bias in the propensity score. So this brings us to discussing the balance, but this might be a good time to take a quick break. But before we go on break, I want to ask Susan if there are any questions. Susan, are there any questions for me so far?
Yes, we had a couple questions come in. The first is, can you combine methods for choosing covariates, such as practical rationale and significant differences?
Yes, and I would definitely recommend to do that. So all of those 4 methods or 5 methods that I listed there, whenever you use one further down the list, you should always speak to the one further up the list. with the exception being the identifying the significant differences, because again, that is sample size, dependent. And so whenever you're using that, make sure you're also using the standardized percent difference.
Great. The other question was from earlier. Does the introduction of selection bias mean that the selection is no longer randomized?
Yeah, actually, it kind of does. And that's a good indicator to show you. So whenever the general rule for randomized controlled trials is that if you have, and if we're thinking about significant differences here, if you have over 5% of the variables that you're observing are significantly different between your treatment and comparison cases, then there's something went wrong with the randomized control trial, because there should be less than 5% of your variables that are different between them if there was if the randomization was actually successful.
Another question has come in. Do you use STATA or R? Or I might be mispronouncing. If STATA, will you talk about whether you use T-effects PS match or PS match 2 and why?
Yeah, so I'm glad that you mentioned that. I meant to mention that at the beginning. I am largely a STATA user, but I also use R a fair amount. I used to use SPSS a lot, and I know we got a lot of SPSS users. And I'm going to try to speak to some of these as we go forward. I do have a slide that kind of breaks down a few of them. I'm not all that familiar with SAS, but I did try to do a little bit of homework on SAS, so I can speak to that a little bit. But I will speak to more of the actual codes in a bit. I will briefly say that I largely use PS Match 2, just because I have a lot more hands-on the ability to change things a little bit more with that. But that said, I'll often go to R and calculate the covariate balancing propensity score, test it all in R, test optimal matching, and then go back, and we can talk about that later.
All right, that's a great lead into the break, folks. We're going to take 5 minutes, go top off your coffee, and be back here, and I'll ask Jason to launch the clock.
Thanks, Susan.
All right, everybody, welcome back to part 2 of today's session. I'm going to ask Jason to revert screen control to Dr. Campbell, and we'll get going.
All right, good deal. Thank you, Susan. Thanks, Jason. So, as I mentioned, this kind of brings us to discussing some of the elements related to balance. So, in our traditional workflow, we can see that after we've fit our initial propensity score model using whatever method we decide is the best, such as a logistic regression, we then want to, of course, assess the initial balance. So what does the balance look like given our new propensity score before we actually apply some propensity score method? Assessing and reporting balance has been an area sorely overlooked by criminal justice research. It doesn't matter if you're looking at peer-reviewed journals or at technical reports. Researchers do not always provide balance statistics, and when they do, they're not the same across the studies. Ultimately, when the treatment is binary, I'm offering you here today about 7 different metrics, but I highly, highly recommend that you use and report numbers 1 through 4 on a regular basis. The standardized percent bias is the primary way in which we can assess balance between the treatment and comparison cases. It's an effect size devised by Rosenbaum and Rubin, who also initially devised the concept of propensity score modeling. I recommend applying it to every covariate, if categorical, then each category of all those categorical variables. Anything over 10% or 0.1 is concerning, and anything over 20% or 0.2 must be addressed. I provide you the formulas here for continuous and dichotomous measures so that you can construct them on your own if you like. That's what I tend to do, is I'll actually manually put these into an Excel file, and so that I can plug in whatever numbers I need and just adjust my typical balance metrics that I report, because I'm not always a fan of what's provided. I know that SAS, Stata, and R all have a form of these in their respective codes, but you should be cautious with this because it may be applying one of the formulas to all of your measures regardless of the type. So just note that there are 2 formulas, and there are different things that they use in those. It's also worth noting that SPSS, unfortunately, to the best of my knowledge, does not provide anything like this. So if you're using SPSS to run propensity score modeling, you might have to do this on your own anyways. So once the standardized percent bias is calculated for each covariate and category, then we need to calculate the overall mean across all of the covariates and categories. Essentially, we're trying to get that average standardized percent bias or average standardized percent difference across every variable that we have that's going into the propensity score in particular. Then you need to find the maximum or the range or the standard deviation. I don't care which one of those you report or all of them, but we need to know the degree to which that propensity score was able to balance all of your covariates. And when it was not able to balance, or the highest the standardized bias is, we need to know what it was. What is the maximum? What is the worst case scenario in this particular pre-PSM relationship? Because we're going to assess all of these again after we apply PSM. You also need to calculate how many, so the percent of covariates are over the 20% limit, and how many are over the 10% limit. So this provides the crux of the balance summary for readers and reviewers to know how different your groups are initially, and ultimately how well you're able to remove the bias. The area under the curve, or AUC, is a metric of accuracy, sensitivity, and specificity of a particular score and its ability to accurately predict a dichotomous outcome. I recommend adding it to your repertoire, although it should not be the only thing that you use, but it can be a decent and helpful tool to show the ability of your propensity score to predict the treatment condition. AUCs over 0.639 is typically viewed as moderate, so they're moderate performance or accuracy, and over 0.714 is strong, according to Rice and Harris. It's worth noting that I've had some reviewers who argue that this is not the appropriate metric, and I think that it is worth using in conjunction with the first four especially, but every other thing that you're using. So it's just one of the many. I'm not saying that you should make any it should not be the make or break decision in using an AUC, but it can be helpful. The prognostic score is the predicted probability of the outcome under the control condition reflecting baseline risk. Assessing the prognostic score is similar to assessing the standardized bias of the propensity score, but focuses on the balance of all covariates in how they predict the outcome by constructing a score based on the comparison or the unexposed group status, and then extrapolating them to the entire sample. It demonstrates the relative importance of each covariate to predict the outcome. Those measures that are most predictive of the outcome should be of your greatest concern because they could create the most bias if left unbalanced. Once you, or while you won't find the propensity, while you won't find the prognostic score in my current published work, I will be using it from now on as much as I can. Lastly, using the Neiman-Pearson approach to interpreting p-values, so the null hypothesis significance test, or the NHST, you can examine the percent of covariates with statistically significant differences. And this is kind of what I was speaking to with the previous question before. After PSM is applied, no more than 5% of the covariates should be statistically significant, which is similar to an RCT, a successful RCT. But you really need to observe this with caution, as the null hypothesis significance test is sensitive to the sample size and standard error estimation. That standard error estimation in particular, after you've estimated the propensity score, is potentially volatile. So hence why it is one of 7 metrics used here. And this kind of speaks to, if you're using logistic regression, if you can use some form of bootstrapping to help with standard errors, that's going to help minimize the concern that you might have. As you assess the pre-PSM balance, you will want to examine how much common support or overlap your treatment and comparison group have between them, given the propensity score distribution. A box plot or density plot, as shown here, can be pretty helpful to see the differences. I provide you an example of each here. The plot on the left is plotting a propensity score using Stata, and the plot on the right is out of R. But you can kind of see how much overlap we have between the treatment and comparison group. And while there might be a fair amount, and that's kind of giving you an indication as to how many cases you might be able to find if you're using a one-to-one exact or one-to-one match, I should say, exact. However, depending on the nature of the treatment and your propensity score application, such as in a one-to-one case, these cases circled here may not have matches, and you may consider dropping or trimming them. Trimming some cases is a common practice in propensity score modeling and should be considered in most cases. However, poor practice is discarding these cases without any examination or discussion. So sometimes, in many cases at least, someone got in the treatment and may have had an outcome that might change your finding. And it depends on how many you have to trim and the size of the treatment sample. So always report the number that you trimmed and then analyze the trimmed cases separately to determine if there's anything you can learn about the assignment or the treatment. A lot of people, especially in technical reports, but on a lot of peer review journals as well, people will say, we lost 10% because they have tens of thousands or so. Well, we lost 10% of cases because they couldn't find a match, and then never talk about it again. Or we lost 20% of cases because we couldn't find a match, and then never talk about it again. It's pretty critical that you talk about those cases again. They got the treatment somehow. What makes them unique? Is there something specific? Could we learn something from them? It's definitely worth a look. So this brings us to the specific propensity score techniques that we might be able to employ. So in our traditional workflow, this is of course immediately following the assessment of the initial balance. And so there are a number of ways to use the propensity score to balance the treatment and comparison groups. The three general areas involve matching, stratification, and weighting. There is no clear best way to choose which one to use, and it often depends on the degree of common support, the treatment to comparison ratio, and the nature of the treatment condition. Remember, we are assuming a binary treatment condition here. Matching is probably the most common and the most well-known and the most understood propensity score modeling approach. It can be easiest to explain when you're thinking to explaining it to policymakers in particular. And I want to, comment on how much I've learned working, especially with the Oregon crew, where we talk to a lot of policymakers and legislators as comparing statistical twins. And I recommend everybody using that type of language when talking about these, especially if you're using one-to-one matches or something like it. When it gets into weighting, it's a little more tricky, but it's still worth thinking about statistical twins. It's easier for someone who doesn't know PSM to wrap their heads around this. So some of the questions that you should ask yourself are things like, how many cases will be lost due to a lack of common support? Which distance metric should I use, the logit or the propensity score? As a quick aside, we talk a lot about propensity scores, and propensity scores are great, but they have a problem when you get to 0. So propensity scores will often clump a lot towards 0, where you have a lot of people with the same propensity scores. But if you use a logit, which goes into the negatives, you might have a little bit more leeway, and you might actually get tighter matches if you end up using the logit. Sometimes people will use the logit and say propensity score, so it's worth noting, that element and the fact that logits are probably a little bit more accurate. So if you're having a hard time finding balance or matches, try using the logit if you haven't already. You should also ask yourself how far away should I allow the nearest neighbor as a twin? So this is talking to a caliper, which we'll speak to in a moment. Should the comparison cases be reused in the sample? So are we matching with or without replacement? What matching ratio should I use? So one treatment case to one comparison case, so that's 1-to-1 matching, or should I use 1-to-many matching? Should I exactly match cases on a specific measure or category? So this is the question of whether or not we should use exact matching versus anything else. So I'll cover a few matching approaches that are some of the most popular or the most common that you'll see in the literature in particular. So starting with exact matching. Exact matching can be understood as one of the best, but also most inefficient matching approaches. It really doesn't need a propensity score itself necessarily, because what you're doing is trying to match frequencies, but there are versions in which you can implement a propensity score in the exact matching protocol. So exact matching in some various forms can be combined with these other methods that I'm going to talk about. Exact matching requires that you find cases that have the same value for the variable of interest. So matches must have the exact same value on key variables. And I circle several key variables as an example here. Maybe we definitely want to make sure that they are the same rates, or we definitely want to make sure that they are the exact same risk level, depending on whatever risk score you use. And in doing so, we're going to ensure that those cases are compared. So if you're using only exact matching, you're going to be kind of limited in the number of variables that you can choose, because you're only going to have so many combinations, right? So it really depends on the cross tabulations, which is one of the reasons why I give you kind of an example cross tabulation here. If you don't have heavy overlap, or if you don't have a lot of similarities between the treatment and comparison cases, then exact matching is going to be rather limited. As the number of matched covariates increases, the number of true twins or matches actually is going to decrease. To address any of the shortcomings of exact matching, you can couple it, as I mentioned, with a propensity score method. Or if you do not have many covariates, or especially if those covariates, all those covariates are continuous measures, then maybe you should consider coarsened exact matching. CEM can be more efficient and precise using exact matches on categorical measures, and then binning or coarsening continuous measures and weighting comparison cases. However, it still can only take on like about a fraction of the measures used in other techniques. So you still can't have a whole lot of measures. But if you have a few, and they're large, a lot of them are continuous in particular, then CEM might be a really strong option for you. I will note that CEM, the creators of CEM, from the folks out of Harvard, will say that CEM is supposed to be a kind of a panacea for people who don't like to recheck the balance and reweight or reassess the propensity score, and I will really caution you on that. It really depends on your specific situation and evaluation. Sometimes it might be really helpful, and it might really streamline the traditional workflow. Other times, I have seen it where it dramatically reduces the number of people or cases that you're actually comparing. So it really cuts down and trims out a lot of cases. And at the same time, you can only use so many measures within that context. Plus, if you're using multiple measures, you still want to check the balance on all those other measures that didn't make it into the CEM. Beyond exact matching, there are a number of ways that propensity scores can be used to match cases and balance treatment and comparison groups. The use of a caliper is highly recommended when using any of these approaches. However, that can cause a lot of a loss of cases, not a lot, but it can cause a loss of cases. It really depends on how many cases you can lose. How many can you afford to lose? A caliper or tolerance level, also known as a tolerance level, so in SPSS, I think it pops up as tolerance level, excuse me, is the set of allowable distance between the propensity score of the treatment and condition. So how far apart can those cases be in their propensity score in order to be determined a matched case? The accepted caliper distance is typically 0.2 times the standard deviation of the propensity score. It used to be 0.25 according to Rosenbaum and Rubin, but has recently been pushed to be a little bit tighter. So thinking about the types of PSM that could be applied, consider the example list of propensity score, these propensity scores for treatment and comparison cases. And this is just an example. I just use this as a visual supplement. It's not necessarily supposed to be indicative of exactly how these mechanisms work. So don't overly scrutinize them. It's just to give you kind of a visual representation. So in a one-to-one matching scheme, this is where you try to find one comparison case for each treatment case. Typically, this involves identifying the nearest neighbor within the propensity score. And if you're using a caliper, then that's going to specifically narrow down which nearest neighbor you choose. So one-to-one matching with a caliper of a 0.03, for instance, would select these cases as potential matches. Most matching is known as greedy matching, which occurs sequentially. Thus, it is possible that a one-to-one matching with a caliper and no replacement will force this situation that you see here. This isn't a problem per se, but you can see that there could be an issue if there were many more like this. So the no replacement and not allowing ties begins to widen the distance between the nearest neighbors, especially towards the end of the block. So once the program starts trying to find the closest matches, it identifies the closest matches, pulls them out of the sample, especially if it's not without replacement, and then whatever's left gets assessed for another match. And those could get further and further apart. So the last few matches that you get, so long as it's still within the caliper, and this is why a caliper is so important, they're going to be further apart than the initial matches that the program found. This is why it's really important for you to set a random seed so at the very beginning, this is an option for SPSS and Stata and R. I'm pretty sure you can do this in SAS as well. But you should set that random seed so that it kind of randomizes that process. And just after, even though it goes sequentially, it kind of randomizes the order of how they are chosen in a little bit of a way that minimizes how greedy matching can impact the distance. If we allow the number of comparison cases to vary, so if we allow ties, we can match multiple comparison cases to treatment cases so long as they're within the caliper. There is still the potential to create more bias by allowing more comparison cases or allowing the cases to be replaced and chosen again. Or best to use a formula to optimize the number of comparison cases to match each treatment case. And there is a formula out there. I recommend using Hansen's 2004 formula. And Austin actually did a simulation to examine how many matches in a one-to-many scenario or a many-to-one scenario would best find or best reduce the bias, rather. And generally, it's between 3 and 5 is what Austin was essentially finding. But Hansen will say that it really depends on your situation. So, what I'll tend to use is both. I'll use the Hansen formula, and if it's way outside of Austin, then I'll try to test both of them to see which one reduced the bias the most and how many cases I was able to retain in relation. But oftentimes they're both in agreement, so it's right on the cusp of that 5 range, or it's closer to 3. This is also known as variable matching. So you're allowing the number of comparison cases that you're matching to vary. In contrast to greedy matching, there is a technique in R in particular, and it should be available as a plugin for SPSS. And it might, last I checked at least, it is available in SAS, but it is not available in Stata, unfortunately. Is what's known as optimal matching. So you can use this to optimize the matching process. And in R, this actual command is called opmatch, and it creates matched cases in a way that minimizes the distance between the first and the last match. So essentially, it is not beholden to the sequential ordering, and instead finds the closest match to each treatment case, in a way that minimizes the overall distance between the propensity scores. When greedy or sequential matching might result in wide distances between the last cases chosen, optimal matching will ensure that the distance between the matches will be minimized using matching with replacement, allowing ties, and choosing matches out of sequential order. The comparison cases are ultimately weighted by how often they're used. Beyond matching, there's stratification, or otherwise known as subclassification. Stratification is somewhere between matching and weighting, and involves balancing the treatment and comparison group by dividing the sample by the distribution of the propensity score. There are multiple ways to organize and divide the propensity score, but generally, as the number of strata increase, the bias decreases with optimal ranges of strata running from 5 to 20. And that was found or at least found in a study by Thomas and Kim, and highlighted in a book by Leach. One of the more popular methods is by dividing the sample by quintiles of the propensity score. Stratification can be employed in two general ways, where the treatment outcomes are balanced and compared to outcomes within similar strata, and you can either pool the strata-specific effects on the outcome, or you can calculate a marginal treatment effect across the strata. This is also known as marginal means weighting through stratification. I highly recommend the work by Hong here. She identified a number of ways to do this and has a couple of publications, the articles of which I've made available to you, but she also has a book out that's really useful. Something to note, though, is that marginal means weighting through stratification is less effective at reducing bias in binary treatment conditions, but works really well in multiple or continuous treatment conditions. Weighting, also known as, or you might see it in the literature as weighting by the odds or inverse probability of the treatment, IPTW, involves constructing a balancing weight that is derived directly from the propensity score. I provide you the formula here because you can choose to and prefer to manually calculate the weights yourself. It's a relatively easy score, and it's something that I often will manually calculate just to check. So if I'm using covariate balancing propensity score, plot that into a weight, and then I can test, just quickly examine certain things related to that. The inverse probability of the treatment, or IPTW, can be constructed for the average treatment effect, while also accounting for any sampling weights that you might have in your data. So if you have complex survey sampling, you might be able to do this in conjunction with those other weights. A clear advantage to weighting is that you're losing fewer cases due to no matches. So you're often everybody's going to get a weight, assuming that this is all aside. This is all assuming that you have addressed your missing data issues. As a quick aside, any case that has missing data on something that you want to, on a variable that you're trying to use in the propensity score modeling, will not get a propensity score itself. So it's important to know that you might lose cases because of missing data, and that's a whole nother issue, talking about dealing with missing data in relation to propensity score modeling. Coming back to this, it's a clear advantage that you're not going to lose cases because everybody gets a actual weight. However, that might bring a bias into the model depending on how extreme the cases are. Some extreme weights may be produced depending on the nature of the treatment and the manner in which you condition the propensity score, such as being a misspecified logistic regression, or you're using logistic regression versus CVPS or something like that. The extremities can be addressed via respecifying the propensity score, trimming cases, which is probably the most common, or changing the propensity score technique altogether, or use weighting adjustments as suggested by leadership. There's been an increase in the interest in treatment effect estimators. So I know there was a question earlier about treatment effect estimators, and Stata in particular has this code called TFX. And this can be a pretty powerful and convenient tool, but we got to remember that these are largely black boxes. They require a strong knowledge about the estimator itself and the ability to replicate your findings. You should know that how the actual treatment effect estimator actually computationally and constructs the average treatment effect and the average treatment effect of the treated and the average treatment effect of the untreated that it provides you ultimately, and which part of the sample it's using. This is often behind the scenes with these treatment effect estimators, but if you're able to tease that stuff out and still examine it and report on it, then there's no real reason why you can't use that necessarily. So they'll often provide you the average treatment effect and the average treatment effect for the treated and for the untreated. So that's one of the things that makes it very attractive. And it's really quick and simple to use. But again, you've got to be very careful with it. And a similar caution is given to all those SPSS users out there who are using propensity score modeling in SPSS. because SPSS can largely be a black box as well. It will give you the data set of treated and matched cases, rather, all the matched cases, but what happened to everybody that we lost? And this is part of the problem, right? We don't know what happened with all those trimmed cases. So that brings us to reassessing the balance. And so this largely has to do with all of the balancing metrics that we talked about previously, but we have to, of course, reassess them once we apply the propensity score. Regardless of the technique you're using, even with coarse and exact matching, you should always check the balance before and after the technique is applied, and you should always report on it as well. This is a sorely overlooked area in the use of this technique. I'll give you a couple examples here of just what the propensity score should look like before, and this is essentially the propensity score that I showed you before in Stata, and then after PSM is applied. You see there's really very minimal difference between the two groups. The most efficient way to assess the balance and report on the balance is to construct two pre and post tables to provide either in text or as an appendix to your report. The first table is the summary balance statistics, which I'll give you an example of here in a minute. And the other is, the summary balance statistics being all these 1 through 7 things, or at least the first 4. And sometimes it's worth noting that a lot of people, or some people, will put in the average propensity score distance as a balanced metric as well. And I'm all for that. You know, the more the better, really. It's just so we can better understand what happened with your data set, what it looked like before, what it looked like after. So the mean propensity score distance is a fine metric. That aside, the other table is provided by or constructed out of a bivariate breakdown of all your covariates. So this is assessed for the balance both pre and post as well, especially those covariates used in the propensity score model itself. Reporting proportions and means and standard deviations, of course, and the standardized percent bias for each of those covariates and categories before and after PSM is applied is quite critical, and I want to emphasize that. So what does this look like? This is an example of how these two tables could be combined. So the top part here is the summary balance statistics that we provided, and this is from one of the examples that I'm also providing as it's one of my studies that I recently got published, but also I've provided that and a few other examples in the zip files that are provided to you after the presentation. So this top part is the summary balance statistics that we just got done talking about, both pre and post match. And then below here, and this is only the top portion of that table, is the covariate balance statistics. And you can see here that this is an abbreviated table, of course, and even in the text, it is an abbreviated table. I provide the entire table of the 337 covariates that we used or compared in an appendix. But you can see that there's the percents of both the groups that we're comparing, which in this case, it's men and women. So we matched men to women, and that's a different discussion we can absolutely have later. But anyways, you can see that we provide the percent bias here for before the match, and you can see how it lines up here, and then after the match. So this is just an easy way for readers and reviewers to digest what's going on with your assessment. So what makes a successful application of propensity score modeling? It really hinges on the overall balance and what you're trying to do. So the standardized bias metrics are the most important. It's critical that we highlight those. All other reported metrics should be considered, and if they're problematic, they should be accounted for in other ways, such as the double robust regression, which we'll talk about in a minute. Be sure to assess multiple approaches before deciding which one is best. So I gave you just a handful of ways that you can use propensity score modeling and matching, stratification, and weighting. But it's really important that you examine as many as you think you ought to before determining which one you're going to report and lean on for your treatment effects. I typically run at least 3 different types. So I'll run 1 or 2 matching techniques, I'll run a stratification technique, and I'll run at least 1 weighting technique, and just compare them on all their metrics, all their balance metrics that we talked about, and ultimately the treatment effect. What is the outcome? What is the effect on the outcome? Are they different between the types? You can see in this example that there are enough areas to assess the different PSM techniques across their performances. In this example, both one-to-one matching with a caliper and optimal matching produce the best overall balance. But before choosing between the two, we should remember who our audience is. So if it is for an academic journal or an academic presentation, report the best overall balance, which in this case is going to be optimal matching. But that might be tricky to explain to policymakers because there is some weighting involved. And they're going to see, they might see in the N, the pre and post N, that they're different. And when in their head, well, I should be seeing 2 exactly the same treatment and comparison sample sizes. Because they both yield essentially the same effect size on the outcome, we can report the 1-to-1 match to policymakers as statistical twins without having to explain the weighting. This is critical to note that if you're going to test all of these, you should definitely note that what you did was tested with multiple types. And if there is no variation in your treatment effect, it's worth noting, right? You know, you tested this with multiple types. And while these 2 were the best, or this particular one was the best balance overall, you really didn't find much of a difference between them. If there is substantial bias, so for instance, the average percent bias is over 10% in your sample after you've applied PSM, consider re-estimating the propensity score model and then testing, maybe in this time, testing quadratics. So the quadratic of age or any other continuous measure that you might have, just test them, see if it increases the accuracy of your propensity score and therefore increases the accuracy of your matching or weighting. And the tightness of your matching or weighting, and also test interactions. You know, I wouldn't go too crazy with the interactions. Sometimes boosted regression will allow you to test up to 8 interactions within it, but it won't necessarily tell you which interactions were most fruitful. And that kind of, to me, is a bit of a turnoff, because if I can't report on it, which interactions were most important in determining the propensity score, then I'm at a disadvantage a little bit, even though I've really maximized the influence. Chances are you're not going to find much of a difference once you land on one that really balances your groups very well. The difference between them is going to be rather minimal. So this brings us to post-PSM analyses. So this is the outcome, and then, of course, sensitivity analysis. If your treatment and comparison groups are balanced, you can examine the effect of the treatment on the outcome pretty in traditional sense. We often rely on bivariate hypothesis tests. So you'll often see, especially in the earlier days of PSM, so in the early 2000s, t-tests and chi-squares will be used, or ANOVAs will be used after PSM is applied. And this is fine. It is plausible that this will give you an accurate treatment effect. However, you need to make sure that these things actually check out. So your mean percent bias is near 0. Your maximum percent bias is definitely less than 10. The percent significant differences, as we mentioned, are less than 5%. There's no additional post-treatment covariates that you need to account for in the outcomes change, and that's pretty much the critical one. That 4th one there is likely not the case, especially in a lot of criminal justice applications. So there's other things that we need to account for, especially if we're thinking about the recidivism example. We really need to have those post-release LSCMI scores, those risk assessment scores that happen after the treatment. If one of these is not true post-PSM, then you need to plan on running a multivariate analysis after you've applied PSM. More often than not, it is generally expected that you run a multivariate analysis on the post-PSM sample to gain the true unbiased effect estimates. Often called a double robust approach, a post-PSM regression is used to clean up small residual covariate imbalance between the groups. PSM can also make the treatment effect estimates less sensitive, which is another draw. Be careful interpreting other measures in the post-PSM regression, as that model is really set up to identify the unbiased treatment effect of the treatment only. So all those other things are somewhat balanced, or they've been changed a little bit. So they're not quite in the exact state that you need them to be in order to interpret their coefficients. That said, you don't have to completely omit their discussion. You can discuss them, but it's not going to mean as much as that treatment effect is. If examining the bivariate treatment, it is expected that this whole time we've been assuming a bivariate treatment, remember. So if this is the case for you, it's expected that you conduct a sensitivity analysis. A sensitivity analysis provides a way to test the degree to which hidden bias, that is the influence of unobserved variables, may have impacted your models and overall findings. Particularly in one-to-one matches, this process estimates how important unobserved measures can be for the findings by determining the predictive strength an unmeasured covariate would have to possess to change the conclusions of the study. So an example in Stata, there's a command called mhbounds by Becker and Caliendo that uses Mansell-Haenszel test to determine the magnitude that the hidden bias must account for in order to change the outcome designated by the measure gamma. The higher the gamma, the less sensitive the results are to hidden bias. Essentially, sensitivity analysis is trying to answer the following question: how much hidden bias would need to be present to alter your conclusions? Gamma is the measure of how much better an unobserved covariate, so a measure you aren't able to account for, would need to be able to predict the odds of being in the treatment in order to change your results. You can think of gamma as factors or odds ratios. So thus, as gamma increases, it indicates how well your findings would withstand inclusion of another measure that predicts the participation in the treatment by a factor equal to gamma. It's a mouthful, but once you wrap your head around this, this is a very, very useful analysis that can really strengthen your findings and your conclusions. I wanted to include this brief breakdown of the PSM and the different softwares that are available out there. So Stata, has these types of commands that are available for these various types we've talked about today. SPSS has these other ones, are SAS. SAS apparently has PS Match. I'm not all that familiar with SAS, but it is worth noting that in the PS Match manual, it touches on all the things that I discussed today. So if you're a SAS user, you might have a one-stop shop. So before we conclude this, really quick, want to touch on some of the developments and extensions of PSM beyond the traditional workflow and the things that we've talked about so far. And a few of these are broken up by what your treatment variable looks like. So staying within the assumption that we've been talking about, which is the binary treatment, there's what's known as Malinobis or Malinobis bias distance matching, which is an alternative to propensity score modeling, which can provide strong balance when PSM can't. However, it's not guaranteed. It uses a different balancing mechanism, which largely relies on a matrix of raw proportions and means for each variable and attempts to minimize the distance between those raw values. Then there's also genetic matching, which is an extension of propensity scores that iteratively, that uses an iterative process and includes Malinowitz distance matching to try to maximize the balance between the treatment and comparison group. I haven't seen much of this in CRIM, and I haven't used it, but I've heard good things in other disciplines such as education. Entropy weighting by Heimler estimates, this is a really new thing, and I haven't seen it really used anywhere except for in a couple seminars. And I've used it myself several times, but it estimates a single weight for each comparison case to ensure balance on all covariates and cases. This is also an iterative algorithm, and I'm still trying to wrap my head around the actual math of this particular technique. But I do use it as a check for my binary treatments analyses because it removes almost all the bias almost every time. It's really remarkable as to how strong this can be, but it's only available in R so far as I know. It's worth checking out if you're already familiar with a lot of these PSM techniques and you sometimes struggle to find balance in really tricky situations. You might want to check out entropy weight. With multiple treatment conditions, you can use multinomial logistic regression to obtain predicted probabilities for treatment conditions. This can be a bit tricky, and I recommend you look into Guo and Fraser's book or Leach's book to learn more about it. In my experience, I've used marginal means weighting through stratification, and it also uses multinomial logistic regression. And it tends to do a great job in removing the bias, especially if you are comparing treatment completers to non-completers or dropouts. I should say treatment completers to non-completers, and you want to include a comparison control that didn't receive the treatment at all. For continuous treatments, I've used and traditionally seen marginal means weighting through stratification used in what is commonly referred to as the dose response literature. Dose response uses ordinal logistic regression and marginal effects to obtain a dose response curve in which you can examine the differences between the initial dose and all other subsequent doses. The only downside to that particular technique in using dose categories that you have to identify and bin cases into larger dosage categories. So this is most prevalent, at least in corrections in sentencing work. If you want to examine the effect of sentencing on recidivism, you'll see a lot of these dose response curves that bin a lot of the years time served together along the curve, and that's because those are the different treatment categories that they used for this particular technique. Covariant balancing propensity scores, however, CBPS, offers a potentially more granular approach to applying the same method for continuous treatment. So if you need more like days or months or something like that, you might be able to use CBPS to actually uncover those types of effects. That doesn't necessarily need bins. So with that, I want to provide my contact information and thank you all again for attending.